So if you want to take it over from here.
Yes. So, so it's my great pleasure to introduce the next speaker, invited speaker at this workshop, who is Jana Kosecka. Oh, excellent, Jana. I can see you now.
Hi.
Hi. Great to see you.
What a wonderful background you have.
So say a few words about while she sets up City.
So can I go ahead and share? Yeah.
Yeah. Yes, please share your screen. Yes. Yes.
Okay.
I'll say a few words about you, and then the stage will be yours. So Jana is a professor of computer science at George Mason University. She did her PhD at University of Pennsylvania and followed by a postdoc at UC Berkeley. She has done a lot of really exciting work on the boundary of computer vision, robotics, and of course, there's also machine learning. She won the Mar Prize for one of her early works on 3D computer vision. And I'm really excited to hear what she has to say today in the invited presentation. So Jana, please, the virtual stage is yours.
Okay, thank you very much for the introduction. So let me try to get started. Can you see my screen?
Yes, I can see your screen. I will verify if it's on the...
All right, so we should be okay. So I want to thank you for the invitation and also the opportunity to speak there. And thanks for the organizers for providing this sort of seamless virtual experience. It's unfortunate that we'll not be able to interact in person, but hopefully everybody is safe and we'll be able to see each other soon. So I'm going to talk about some topics which are related to localization and SLAM, but I would also like to sort of branch out a little bit and talk about these a little bit more broader questions of generalizable visual representations, which could be also used for a variety of tasks. So we are in exciting times these days. There have been a lot of technological advances made by which sort of spun out of SLAM-related research. Many of them sort of fall into these categories of visual or multimodal visual odometry, where we have sort of vehicles or unmanned aerial vehicles able to do localization and mapping in challenging environments. I'm going to primarily focus on visual modality, but there are other sensing modalities which are being used in order to successfully solve this problem. And sort of the early incarnations of these technologies have been exploited in the street view mapping application, where the focus was more on trajectory recovery as opposed to 3D modeling. Then we have these techniques also sort of affecting the developments in the AR and augmented and virtual reality, both on the cell phones, where sort of the camera tracking and local understanding of the environment is very important. And also it's sort of the AR setting for HoloLens, where we sort of need to understand how the head moves. So I would like to give you a little bit sort of my view of the components of these problems in order to sort of set up where my talk fits right now. So there have been a lot of efforts in development of techniques for visual odometry, basically trajectory tracking being vehicle or camera. And these sort of came along with different representations of the environment. And usually we had, there's always desire to get more robust solutions, but we have sort of good understanding how to jointly optimize the visual odometry given certain choices of representation of environments. And the most commonly used are the key point, point clouds, voxel grids, side distance functions. Right? And these typically work locally well, but if you want to kind of scale up, you encounter some drift issues, and this is where the need for some global constraints comes. And the global localization aspect, there both needs to get kind of global geometrically consistent trajectories if that is what you desire. But if you do not strive to build these large-scale consistent maps, these aspects of global localizations are also related to kind of place recognition or semantic localization, where you may want to just localize given a single view where in the environment you are. And so for majority of these approaches discussed here, usually the localization or the visual odometry or the 3D model building is the final task which is being considered, and or the camera tracking. And so what I would like to do today is to kind of discuss some different ways how to look at the problem by considering different type of tasks which are more relevant for robotic settings, such as, for example, navigation or object search or reaching a particular target or human-robot interaction, and think that maybe if one considers these various task constraints, one can relax a little bit the requirements for very precise localization or requirements for kind of dense, geometrically consistent and metrically consistent models, and use some of these data-driven and learning techniques to sort of overcome some of the brittleness of the previous techniques. And also hopefully generalize some of these strategies to previously unseen environments. But before I proceed, I want to sort of give you a little bit of history, just so you kind of see my path, how I arrived to my current interests. So we have worked early on various aspects of visual odometry, and it is fair to state that if one can sort of achieve a reasonably stable feature tracking using key points across the frame, this is usually satisfactory given some additional constraints and proper optimization techniques to recover the pose of the camera and the trajectory over sort of local or semi-global area. And then if one encounters some drift, some global loop closure constraints can be deployed. So we have done some early work in visual odometry using panoramic cameras, and this is sort of well known that if you have a wide field of view, this problem is actually really well conditioned, and usually you encounter very little drift. And so historically, once you have the good poses, the 3D reconstruction problem has been considered separately. So these are some examples of some multi-view stereo techniques using the registered poses which were recovered using the visual odometry. So this is an example of basically being able to recover a fairly high quality piecewise planar model, assuming that the poses of the camera are quite accurate. So in case the feature tracking and the visual odometry fails, which we always know that it is possible, and most commonly encountered failures are the ones where you have extremely low textured environments, or sorry about that. When you have low textured environments where you cannot successfully match the features, there have been several approaches how to bring richer image representations into the final optimization process when it comes to pose recovery. And we have also done so where we're looking at mechanisms how to exploit a single view reconstruction and piecewise planar structure of the environment, which you could fairly reliably estimate using these data-driven machine learning techniques. So this is sort of this single view Manhattan layout where you can basically get this watertight model of the environment. And then we looked at ways how to actually integrate these models over time and build sort of high quality watertight models of indoor scenes where we would use the trajectory tracking only in the translation space, and as well as the global graph slam optimization was then significantly simpler because the rotation estimates were obtained from the single view. And so this enabled us to obtain fairly high quality models, which were watertight, coarse, piecewise planar structure models of indoors environment. So we were basically looking only at the layout of the environment as opposed to the detailed structure. And this worked fairly well. So this was an example of bringing sort of stronger model structure in order to help the post-optimization process in situations where the key point features were not reliable in order to enable the tracking and the reliable post recovery and reliable loop closure constraints. So in recent years, there have been a lot of advancements, mostly propelled by the development of object detection, semantic segmentation, and recognition using these data-driven techniques where we can sort of train large, deep neural networks, which can estimate. We can train in a supervised manner the large, deep networks, which can estimate per pixel labels of sort of important categories, both for indoors and outdoor scenes. And along the way, we can also estimate the depth of the scene. So we have also looked at some approaches where we can look at strategies where we can estimate the semantic segmentation and depth jointly, sharing a common architecture and understanding how the depth estimation and semantic segmentation interact. And this was simply a training, kind of a big U-shaped neural network where we were both optimizing the semantic segmentation loss and the depth recovery loss. And so this is just a visualization of some weight sharing between the network, which does the semantic segmentation and the depth recovery. And we have been able to demonstrate that sort of they favorably interact in the sense that the depth recovery actually helps the semantic segmentation. And this was sort of our final evaluation criteria, which we used. So this is just kind of bringing a little bit bits and pieces of the previous work in. And so these advances enabled sort of big progress in fairly high accuracy semantic labeling, both for indoors and outdoor scenes. And so here are some examples on NYU data set where you have the scenes, then in the second column, you have the ground truth information, and these are the estimates by using our model. And then in the fourth column, we have the raw depth data, and this is the depth data estimated by our model. And this work is 3 years old. So since then, there have been a lot of advancements made in order to have a better depth recovery, sort of properly following the depth discontinuities, using sort of more sophisticated priors and so forth. But so what is nice that one can actually achieve this using this sort of single architecture. So and this sort of works well both in indoors and outdoor settings. So the semantic segmentation in the localization and SLAM community has been long recognized as very effective in sort of helping to overcome some of the challenges when it comes to large variations of viewpoint, weather, or time of the day. And we too had some early work in this area where we used the semantic segmentation for the problem of location recognition, where we simply used the traditional bag of words representations, which were sort of augmented by semantic information. And this is also, these ideas have been also around in the context of autonomous driving. So basically you take some geometry and some representation extracted from semantic representations, and this helps you sort of bump up the accuracy of the image retrieval, which then sort of consequently serves as a place recognition. And here are some examples of being able to correctly recognize the building across big variety of query views, which vary across the time of the day and season, and the fact that the building features were matched to building features based on the semantic information sort of helped significantly. And these are some variations across the season. So this is sort of these bits and pieces which different lines of research brought together, and people have really made a sort of a big headway in building these rich spatial representations of indoor environments where you can have the correct geometry, you have semantic labels, you can have information about objects and their poses in terms of 2D and 3D bounding boxes. And in certain cases, this information, these representations were jointly optimized with pose recovery. In some cases, the pose recovery was considered separately, and then the post-processing was done using these 2D segmentation techniques or object detection techniques. So what I would like to do now is to transition slowly and ask a question. Well, so a lot of the motivation when it comes to robotics and robotic tasks, so these spatial representations, which we have been sort of striving to achieve, were to some extent consistent to the type of representations people use with navigation and control, right? So you typically, in a 2D case, you have 2D occupancy maps. For a 3D navigation, you can have 3D voxel grids or 3D occupancy graphs, maps. You can have continuous representations of the environments, which can be approximated by some graph structure. And so this was essentially the interface between the representations built by perceptual component and make this representation amenable to the follow-up motion planning and control. But majority of so this was basically the interface, but majority of the motion planning techniques typically assume that the model is given. So in order to facilitate this interface between the perception and control, one would have to invest a lot of energy into building these accurate models before one could use these models for planning and control. And so what we started looking at and thinking along with some other researchers is that whether we can sort of overcome a little bit some of this brittleness of these interfaces and needing to actually build the complete models before we can use them for navigation, and see whether you can use some of these data-driven techniques to learn the navigation strategies directly without building 3D models, and then sort of consequently basically learning the right type of representations in order to facilitate the different navigation tasks. So let me kind of very broadly define this task of semantic navigation. So we would like to have robotic agents which operate in dynamically changing environments over extended period of times. We would like to learn a certain set of skills such that they can carry out a variety of flexible tasks, follow directions, and communicate with humans in natural language. And we would like to identify navigation skills and learn them in a robust manner such that they can be easily generalized to previously unseen environments. So the generalization aspect here is sort of quite important. And of course, you can imagine that if you could do something in previously unseen environment, then over time you can sort of improve and then gradually build the model of the environment and update the model of the environment in order to carry out your navigation tasks reliably and effectively. So let's have a look a little bit at what the ingredients of this semantic navigation may look like. So imagine that you have a robotic agent who you would like to instruct the agent to go to the refrigerator and open the refrigerator and get the bottle of milk. So in order for the agent to be able to do this, you need to have some ability to know where the refrigerator is. So the ability of detecting objects and their pose, because you need to know where the handle of the refrigerator is in order to be able to do this, is really critical in order to be able to figure out what the goal of the agent is. And this is only in the setting where the agent is visible. Then you need to understand a little bit what is the free space, what the obstacles are, maybe understand the context, whether you're in the kitchen or in the living room, and then be able to plan a safe path in the free space. So what I would like to do now is instead of focusing on the problem of localization, which is the where am I problem, and it is really sort of central to the problem of mapping, I would like to sort of focus a little bit on the problem of how to reach the goal. And perhaps we can come up with some strategies how to do it without necessarily knowing the initial positions, without necessarily knowing the exact localization. And we can explore different ways how to specify these goals. And you can imagine some intuitive motivation for tasks like this could be, imagine that you have visited, I don't know, 100 apartments, and you know how to find a refrigerator. So when you come to a new apartment, which you have never seen before, you should have some prior knowledge, which should help you how to go and explore that environment in order to find your goal. And then along the way, maybe build a better map of the environment. So this is one way how to think about these policies, which I'm going to describe this, and how to relate them to some of this mapping and localization work, is to think of them as these navigation priors, because clearly they're not going to perform as well as the approaches where you have a perfect map and you can plan the trajectory, but they're a good starting point. And these are sort of a lot of open questions for current research, how to continue. Okay, so let me sort of go back a little bit and review some historical work, sort of trying to understand what are the meaningful skills, right? Because in traditional motion planning, one does not typically consider skills. You know, you have always sort of starting point, goal point, and you need to find the collision-free path. But if we want to think about it as the skill perspective, we can sort of consider two different categories of navigation skills, and they require different level of sophistication when it comes to models of the environment or availability of the maps, and then also to what kind of maps do we need. So one class of navigation strategies are so-called local navigation strategies, and they fall into the following categories. They can be search, route following, so following a path which you have previously explored, or aim to reach particular target, or reach some relative position with respect to the target of interest. Another class of navigation strategies are topological navigation or survey navigation or some recognition trigger navigation, which require a little bit more detailed representation of the environment. So let me give you sort of some feeling for what this may look like. So the search, you know, the simplest form of search is just simply random exploration of the environment until the goal is reached. Another local navigation, and of course, there can be a lot of additional constraints which one can impose on the exploration strategies. Another type of navigation skill could be direction following. So for example, if you have traveled a particular path or particular class of path, can you repeatedly execute the same kind of behavior in different environments? So these are sort of either variations of following exactly the same path in previously seen environment, or having strategies like corridor following, where if you know how to follow a corridor and turn at an intersection in some environment, that you should be able to know how to do it in previously unseen environments. Then there are these aiming strategies. So if you have some salient goal, be it a view or object of interest, you can learn an ability to do some relative positioning strategies. So given some initial view of the target, how to reach some desired view of the target. And you can do this for objects or views, or you can do it also for locations which are specified using some spatial relationships between relative objects, which could be some interesting landmarks. So there's a big variety. There's of choices one can consider here. And then the global navigation skills are the kinds which require some sort of map. So if you have some starting point and the goal point, you may have some ability using some topological navigation to find sort of intermediate location to pass through. But as long as this door is closed, then you need some planning ability in order to replan. And in order to do this replanning, you really need some more detailed spatial model of the environment. So you need to kind of know how to return to the place which was your original goal. So this is just to at least sort of briefly outline some of these different levels of skills and granularity and how they may affect the representations of the environment. So let me talk about what we can do when it comes to navigation, this very local navigation where you just simply want to reach a particular goal. So if the goal is in the field of view, and you have some desired relative position with respect to goal, which you want to reach, this is basically a traditional version of a visual surveying problem, which could be accomplished by establishing correspondences between the starting view and the target view, and then designing the control law, which is governed by the laws of perspective projections, in order to calculate the linear and angular velocities to reach the goal. But as these correspondence techniques typically go, this type of controls are very brittle. So as long as you lose the correspondences or you cannot establish the correspondences properly, these techniques fail and they are very brittle to this when it comes to this process. So we've looked at strategies, how we can actually take some of these initial representations and the learned correspondences derived from these mappings in order to learn this goal-reaching policy. And so here is a small visualization of the initial view, then the target of interest, and the final view, which the agent is trying to reach. And so let me sort of discuss a little bit the approach. So what we have done is we basically have taken the current and the target view, and using the depth map, we have computed the exact correspondences between the two views. I mean, exact modulo the errors which one attains on the computation of these correspondences. And we use these correspondence maps as an input to a deep learning network, which was a mapping between the correspondences and the control actions. So the perception component directly have taken the correspondences, and then we basically use the deep Q-learning in order to learn the probability of all possible actions. So we have considered a discrete version of the problem. So this is also why the motion is a little bit jagged, because the space of actions is discretized. And so we were able to show that this representation is sort of suitable for these local aiming tasks where the final view or the target of interest is already in the field of view of the agent. And this does not require any localization or knowing where the agent is with respect to the goal, as long as the goal is visible and some goal keyframe is specified in memory. So we have trained this policy by sort of sampling various configurations of initial and final views for different targets in Gibson environment. And we have, so this was an experiment which we carried out only in simulation. And we have demonstrated that by learning this policy, we have attained a navigation skill which was much more robust than the traditional image-based visual surveying, which was sort of relying on this sort of precise correspondences. So in some sense, the network somehow managed to pull out the relevant information from the correspondence map at the places where it was reliable in order to come up with the right kind of commands. And this was presented, this was a work of my student Yimeng Li, and it was presented just last week at ICRA. And we have done some comprehensive evaluation of these strategies for a variety of target views and targets. So this was the first setting where the target is already visible. So the second question is, well, what can we do? I mean, how would the navigation priors look like if the target is not visible? So here the question was, can we have these target reaching behaviors at the level of that you will drop the agent somewhere in the environment and you will say, go to the refrigerator or go to the microwave, and then agent will basically learn a policy, which is a mapping between the observations and actions in order to achieve this goal. And so we have considered this semantic target-driven navigation tasks for several targets. So we looked at sort of couches, microwaves, refrigerators, and the choices of targets was really mostly related to the availability of the training data for a particular class of targets. And so before I sort of discuss our strategy, I want to just briefly mention that this is something which has been of interest to several people in both robotics and vision communities. And previous approaches sort of try to tackle the problem by learning the mapping directly from images to actions using different architectures and different sort of mechanisms for supervision. Usually the approaches were formulated in the reinforcement learning framework, where the choice of the reward was usually choice of the reward structure was quite challenging because these type of problems typically require a large number of trials, and with sparse rewards, it's very hard for these policies to converge. So without sort of trying to relate it to all the work on reinforcement learning, I'll tell you sort of briefly what we did is, so instead of learning these mappings directly from images, we have opted to actually use as an input to this policy semantic representations extracted already from the state-of-the-art available object detectors and semantic segmentation. So the input to our navigation strategies were object detection masks, semantic segmentation masks, and depth map. And these were trained using the state-of-the-art data sets in the supervised setting. So we used COCO to train the object detector, and we trained the semantic segmentation on NYU data set. And then we've learned a policy where we learned a common embedding of these three semantic modalities followed by some fully connected layers in order to predict the action. And the first order policy was just a feed-forward reactive policy, which we then sort of later on improved by adding some recurrent component. So I will discuss the recurrent component in a little bit, but before I proceed, I want to sort of discuss a little bit these aspects of training and evaluation when it comes to learning policies, which so we have used the Activision data set, partially for the training, in order to be able to sort of understand and work with the real images and real depth data. So this is a data set which was sort of put together through our collaboration with the University of North Carolina, and Phil Amirato is the main force behind the data set. Phil sort of went and scanned 11 homes. There are right now about 30,000 images where you have 12 views per each location, and the locations are about 30 centimeters apart. And the entire home is fully registered. So we use the call map to register the views. So here at the bottom, you have visualization of all the registered views. And the nodes are the locations where the 12 scans of the environments were taken. And per location, we have both RGB and the depth data. So the data set is not very large, and it's certainly not sufficiently large in order to train these complex navigation policies. But here are some samples of the models of the environments. But we have been sort of successful in training it jointly with the simulated environment. And here are some examples of some of the training mechanisms. So we have simply, instead of training it in a reinforcement learning setting, we've used the imitation learning, where we have generated a lot of ground truth shortest path from arbitrary points in the environment to the goal. And this was serving us as a supervision. So we could then tell at each instance of time, we could give, so what we would like to do is we would like to predict an action which has the highest probability, which would be the action which would reduce the distance to the goal. And you can either do not reduce the distance, you can move further away from the goal, or you can move closer to the goal. And that was basically per state reward, which we could do to our system. So you can also think of it as being able to give the model extremely dense set of rewards, as opposed to just waiting for the reward once the agent finds the goal. And this was facilitated by this ability of computing the shortest path using just a simple Dijkstra's algorithm on this discretized navigation graph. So the first attempt was just to come up with the purely reactive strategy, and then the second improvement we have achieved by adding a recurrent component, which provided a little bit of a memory. So the way how these policies looked like, you give it as an input the semantic representation of the environment, and as an output the policy, you will learn the action. And I'm not going to go through the details of the performance. So we have done very detailed ablation studies on what matters in terms of semantic segmentation depth, image-only object detectors. And we further improved the training by using this joint training between the real data and the simulated data, which also significantly improved the performance. And the appeal of the approach was that because the representations which we used were semantic, we didn't really have to deal with this real to sim transfer and photorealism issues, because the models were basically trained using these higher level representations. So these are some sample training runs in simulated environments where we use the House 3D simulator. So here are some examples of the difference between the simulated and real data. So this is also sort of an important issue to consider. So the real data are significantly more noisy than the simulated data. So this is sort of something to keep in mind if one is learning the policies in simulation only. And there has not been sort of a thorough study to what extent these errors actually affect the navigation strategies, but this is a sort of definitely interesting question to look at. So here are some examples of some of these, some of the policy in action. So here is an example of target being couch. So you can see that the agent started in some random environment, looked around, realized that it's in the kitchen, and then it started heading down the corridor. And once it's found the couch, it started heading towards the couch. So basically, the policies learn some kind of semantic content, which enables agents, you know, if the agent is in the contextually wrong environment, looking for the target, which has never been seen in that previous environment, it typically leaves the room and starts exploring sort of other areas of the apartment. Here are some other examples of going to microwave and refrigerator and looking for TV. So you can see that at the beginning, the target is not visible, but eventually the agent finds the target. So this was sort of exciting and promising, but as you can imagine, from the robotics perspective, the results were in some sense disappointing, but not surprisingly, because again, we were sort of measuring the performance on previously unseen environments, and we were simply measuring the success of single episodes. So there was no exploration, no memory. It was just purely reactive behaviors. But despite of the fact, the method was significantly better than random, which would be the random exploration, which we would have at our disposal if we were not learned the navigation prior. And in 55% of the cases, we have found the goal within, I think the episodes were within like 30 or 40 steps. So the next follow-up of this work, and I'll probably start going a little bit faster, we started late, was sort of trying to understand if we were to have a map, if we were to build a map in the process, whether that would help, right? Because this reactive strategy, you know, has a little bit of a memory, but there's no notion of a map, right? And so we have extended this work in order to incorporate a mapping component. So what we have, and also the localization component. So what we have done is that we have basically adopted the MapNet architecture, where instead of using the right features for localization, we use the semantic inputs both for localization and mapping. And so the way how the final architecture looked like is that we would give it as an input image, output of object detectors and semantic segmentation. We will build a 2D map. So where we would, at each instance of time, estimate the position of the agent, and each location of the map grid would have some learned embedding associated with it, which was learned from the semantic features. And then this map was then used as an input into the navigation strategy. So as opposed to just using an input image, you would also use the map in order to train the strategy. And so there were two components. We had sort of parts where we trained both of them separately. Then we had some experiments where we fine-tuned the models. But the essence was that the mapping indeed helped. And with the mapping, the performance of these target reaching navigation strategies improved significantly by some percentage. Okay. Again, mind that this is still just the evaluation of the single episode. There's no kind of there's no map building component. This is just improving a little bit the memory component of the model in order to improve the success rate. And we have done some experiments, both again on Activision dataset and Matterport dataset. So, and here are some visualization of these experiments as the 2D map is being built. So this is, you can see on the left is a bird's eye view of the map and the path the agent is following. And this is for reaching the couch. And here is for reaching the TV. And here, the 2D map is just simply occupancy grid, and the coloring is just the projections of all the 3D points on that particular occupancy cell. and it's sort of colored with, you know, the color of the points. So this is sort of some attempt to, again, learn a map where the information associated with each occupancy cell is optimized for localization and navigation, target-driven navigation task. Okay. So let me sort of slowly wrap up here. So another interesting experiment which we have sort of carried out in the context of this Activision data set is active object recognition. So in the robotic settings, the state of the art of the current object detectors dramatically varies and is affected by the amount of occlusion and viewpoints. So there are a lot of opportunities for developing active recognition strategies where the agent actively changes the viewpoint. And we had some initial attempts to do so in our initial dataset paper, and I'm not gonna go to details, but again, this was a policy where we were optimizing the recognition rate, and it was again trained in reinforcement learning setting. Another important component, which right now it's sort of not fully integrated into these pipelines, is the object pose recovery. So I'm a firm believer that the world is made of objects, and we really should seek some strategies where we can jointly recover the 3D pose of the object and integrate it into these sort of aiming and pose estimation strategies, and both in the context of localization and mapping. And we had some initial attempts how to do so in cases where the pose, so this was in a supervised setting when we were trying to estimate the 3D bounding boxes of objects, and we had only pose annotations, ground truth pose annotations in images. So for this type of approaches, one requires extremely large number of training data, and we have already heard some other techniques which have been very successful on this workshop, which, for example, use the CAD models in order to pre-train the techniques for pose estimation. So there is sort of this whole spectrum of choices and representations one can use in order to tackle these problems. And I will just fly through this. There is a reference to the paper. I'm not going to go through the architecture. And I would just like to wrap up and maybe open to questions. I think this avenue of thinking about the tasks and which the environments will be used for sort of opens new avenues, how to think about what are the right kind of representations for the environments. In many cases, one can relax the assumptions of requiring exact localization, because now we are trying to tackle these tasks without requiring exact planning and control, but we can sort of learn these different navigation skills. Then, of course, the question is how we put these navigation skills together in order to accomplish these more complicated tasks. So I think I'm just going to leave with a lot of open questions. I think there are a lot of interesting avenues to pursue, especially when it comes to representations which use objects and pose jointly with semantic segmentation and depth. So, and I want to thank my students and collaborators and the organizers again. So thank you.
Jana, thank you very much for the exciting talk. Thank you. I'll do this virtual clap. So there is several questions on from YouTube. I'll maybe start with one of my questions. So this is more, I also have this motivation of going eventually to real robots, maybe going indoors around hospitals, for example. So how big do you think the gap is from doing these experiments in simulation towards maybe running some kind of a system like this, which can navigate in a, say, hospital or in some kind of a real robotic platform? Do you think this will generalize directly? I'm sort of more thinking of this generalization rather than, of course, there'll be issues about the platform and stuff, but do you think the visual systems will generalize?
So I think I would definitely not deploy a system like this and expect it to generalize. But I think about it more as navigation priors, right? I think, you know, when we are deploying these systems in real robotic settings, we should exploit all the constraints the environment is offering us. We should really try to build high quality maps as we go along and operate in these environments, because, you know, that's what we can do. I mean, if you buy a robot, you know, it will be at the end operating in that hospital. So these sort of mechanisms for building kind of robust metric, spatially coherent maps are, I think, meaningful. But I view this as this type of approaches as sort of some alternative in order to overcome kind of the brittleness of the other techniques, right? Because we all know that, you know, when these techniques fail, they fail really sort of badly, right? And so you maybe want to have some mixture where you sort of have something where you are building the map, but you have these kind of skills and recoveries that you can kind of recover and get back to that mode without sort of completely giving up. So I think a lot of these problems are, I think, motivated by this sort of holy grail AI questions of how perception, control, and planning interact. So I think this is one aspect which is, I think, really interesting. But I think the impact of these policies is also on being able to deal with dynamically changing environments, such that you don't have to sort of constantly, you know, rebuild the models, but you can adapt them along the way, right? So there are a lot of, I think, possibilities to explore along the way.
It's very interesting. Actually, Devaraman was recently also saying this idea is that somehow the learning-based techniques sort of seem to fail more gracefully compared to the standard structure from motion. It's a very interesting property, which I think is
I agree. Yeah. Because, you know, I mean, if something is all resting on like 5 correspondences and you just only find 3, then there's nothing. I mean, so of course, exaggerating, but yes, so I think they provide sort of some systematic way how to build in a little bit of robustness without kind of hand coding and fine tuning things.
So ask them one more question from the YouTube. So the question was, how can we generalize this kind of navigation approach to continuous action spaces? Which I think is an interesting one. Can one go, how would one go, or have you thought of going to more continuous action spaces?
Yes, so there are sort of 2 avenues. So one avenue which is being pursued. So the problem with the continuous action spaces is that it's not trivial to get the dense supervision, right? Because you would have to basically solve the optimal control problem. So there are 2 sort of avenues people are pursuing. Either they just go with reinforcement learning. So you basically, supervision is sparse, you do what you can do, and then you get a reward at the end. And in order for these techniques to work, they need to usually set up a lot of auxiliary tasks in order to introduce more structure into the problem. And usually the auxiliary tasks are reconstruction, detection, you know, all the tasks which in some sense our representations are sort of offering. Another avenue is to, you know, have some mechanism where you still provided the supervision using these discretized representations, because shortest path is easy, but then have it kind of executed using continuous representations. So this is sort of something we are currently exploring in order to be able to have better level of supervision and stick with some combinations of this imitation and reinforcement learning. And at the same time, remove this jaggedness, which sort of currently exists in the resulting control strategies. It also depends a little bit how the goal is specified. You know, when the goal is specified in the egocentric coordinates, then you actually have an option of deploying these optimal control techniques because you know where the goal is. But these techniques then require localization, right? So you typically assume that you're perfectly localized. So there are these, pros and cons, and I guess we need to explore different angles to figure out what works best.
I'll ask maybe the last question, which is, I think, yes, please go on.
Oh no, I just wanted to say that I believe that, there are a lot of, I believe that there is an opportunity to have many of these skills, right? So because there are a lot of different ways how we know how to navigate, but then the problem will become, how do you decide which skill you utilize if you are tackling more complex tasks?
And so I'll finish with last question, and it's related to semantics. Actually, there are sort of two related questions in the YouTube chat. And I think they are sort of more related to the sort of first parts of your talk. But I think actually this sort of idea of using semantics has been reoccurring through your talk. So I will kind of ask more general question, wrapping all these together. How do you think these approaches sort of generalize? So the question here is, well, if you train it for outdoor semantics, then, how does it generalize to indoor scenes? Similar to viewpoint, how general it is with respect to the viewpoint. So, can you maybe say a bit about the semantics and how do you see it sort of being used, and the idea of generalization between different spaces? Like you have to retrain.
So indoors, outdoors, it doesn't general. Right. So one needs to consider just meaningful classes of the environments. Now, what the semantics does is semantics is tricky because on one hand, it reduces some of the specificity, right? So sometimes you can actually lose some of the information when it comes to localization. But because you have these models which are trained for categories which have large variation in appearance, viewpoint, and lighting, these are the main components which the semantic information sort of helps you factor out when it comes to brittleness of these systems. But again, it's a tricky part because, for localization, you can have semantically identical places, but they can be very different. So at some point, you need to have these different levels, right? You have a semantics, but then you have either the geometry or appearance underneath, depending on what you are looking for. But I would definitely not expect these things to generalize across different environments.
Yeah, yes. Okay, so Jana, thank you very much for this exciting talk. Thank you very much again. Thank you
for having me. Okay, good to see everybody. Thanks.
Thank you very much.
Okay. Stay healthy and safe. It must be late for you.
Yes, you too.
Not too bad.
Yes, you too. It's okay. It's okay.
Okay. All right. Thank you.
Thank you. Bye.
Goodbye. Bye.
Kristen, please.